Today, our topic is news from the InChI, so from the International Chemical Identifier. And herefore, I will explain some news, what's going on there, because we get more and more involved into the InChI group. It is getting us into the InChI community, I have the impression. And I'm really happy to welcome Dr. Gerd Blanke from Structure Penium, who's also the technical director of the InChI Trust. So nice to have you here, Gerd. We have tried to summarize the developments from, I would say, 1 year of intensive work within the InChI. And for those of you who are not so familiar with the InChI, just some words of introduction. So what is the goal of the InChI? In fact, the InChI goal is to create a free, non-proprietary identifier for chemical substances. Perhaps some personal comment, why is free so important? I mean, you also know the CAS, or the CAS, the CAS number. And if you have a compound, then you can register for a CAS number, but this is not for free. And on the long range, it is important to have an identifier for all substances, which should be free, and also for substances which do only exist, in theoretical calculations, perhaps in the design of an experiment or in the chemical planning, but not yet as a real substance which you can lay on the bench. So in fact, a non-proprietary identifier for every substance which is thinkable, I would say, is really useful to find and link chemical and biological data, and also useful for data compilation. So perhaps on the long range towards machine learning. And in fact, there is so much chemistry published over the years, there's so much chemistry on the web, and it's really important to connect all this data, because sometimes a chemical is called, how can I say? There are so many trivial names for some chemicals, especially in organic chemistry and pharmaceutical chemistry. It's important not just to have some trivial name like aspirin, for example, but to link chemicals by a systematic name. And linking this information gives a new knowledge, hopefully. And here's now the connection to the FAIR project, because on the long range, the will help to make chemicals fairer. I mean, we're also collaborating with NFDI for Culture, for example, and also other NFDI consortia, and they can use text engines for text mining to scroll through Goethe's Faust, for example, or works of Schiller. So there are enough instruments in the meantime to go through text and mine text. But in dealing with chemistry, you always have the problem that chemicals or the chem draws are not just figures, but they are metadata in itself. How is the connectivity, the topology of molecules? And to make the molecules findable, to make them fair in a FAIR, in the meaning of the FAIR criteria, to make their data accessibility and also interoperable and reusable, it's important to link all this information. So reusing the data is only possible if you have a unique identifier. And so the metadata include also the qualified references to other metadata, which means that the InChI is really is part of the important metadata. Okay, and the InChI is not just there for academia, it's not just there for industry, it serves all, it serves the whole community. I have the impression that sometimes industry is more interested, sometimes academia is more interested, but linking all the data is useful for the whole chemical community. Say it may be something like the FDA, for example, which has to deal with new drugs, for example, or new poisons. Or new companies which are dealing with patents. So all this needs to be tackled by a useful molecular identifier. What's now the key about this? InChI is a structure-based identifier that is unique and non-proprietary, which means by drawing the structure, you should be able to calculate by some code behind, we'll talk about this later, the InChI. And in fact, the InChI key is a hashed version of the InChI, which allows for a compact representation, which is more useful for the for search engines. So for example, the InChI consists of different layers. The first layer just says 1S, this is a standard InChI. There are also non-standard InChIs behind, but the normal user does not use them. Then you have the chemical formula sublayer, here shown in red. So for example, for this molecule. Then you have the atom connection sublayer here in yellow. Then you have the hydrogen atom sublayer. So how many hydrogens are sitting where? Then a charge layer. So this is positively charged +1. Then you also have the possibility for further layers. For example, the sterol layer, or you have also for isotopes layer. So there are different further possibilities, but this is a small molecule. So the InChI is not super long. but the InChI key is then a compressed version, I would say. And if you put the InChI key into Google, you immediately find all the information you need. So for the not only Google, I don't want to advertise it, but also for other search engines, the InChI key is a little bit more practical. Okay, the problem is what you already see, the InChI string is not designed to be readable to a normal human. So who's thinking of the SMILES code? The SMILES code makes the appearance of small molecules that you can understand it as a human. But the InChI, I think, is not really good readable or not well readable for humans. I mean, Gerd, who is dealing with the InChI so much, I think he can just by mind translate from the InChI towards a molecule of small molecules, but it is rather designed to be machine readable. And in terms of artificial intelligence, it's important to have machine readable possibilities. So it's similar to a QR code or to a barcode. Okay, going a little bit further, is InChI a success? I mean, yes, we can really say this because there are so many databases out there and they have millions of molecules. So for example, the EBI Unichem database, 157 million compounds, or PubChem, I mean, in the academic world, PubChem and ChemSpider and Reaxys are really intensively used. And there are so many millions of molecules which are noted with metadata by using the InChI. So this means the InChI is really, really useful to connect this data. There are also virtual databases for drug design using InChI keys, and also the human genome database is working with the InChI. In this case, it's really working well, I would say, because it's a mainly organic substance. And so this is really a quite established chemical identifier. And going over that a little bit more, although it is now existing for more than 20 years, the InChI is not yet fully sufficient. I mean, as I just made some advertisement, it is really good for all the databases, but from the viewpoint of an inorganic chemist, there are a lot of shortcomings because inorganic compounds cannot be really well dealt with. That's a problem which we discussed last year really in a lot of meetings. And there are also points where the InChI has to get better. Well, this means that there is an active InChI subcommittee of the IUPAC Division 8. And the InChI itself is then divided again in working groups. And these working groups then are dealing, for example, with extended stereochemistry. The organic people have some wishes in stereochemistry. So R-trope isomery is still a problem. And inorganic stereochemistry is a huge problem where we have still to work on. And then, for example, working on tautomers, it's difficult. Isotopologues or large molecules, thinking about polymers, for example, it's also some challenges. Using monomer atoms, I think Gerd will tell a little bit more soon. Then, and we are also part of the organometallics inorganics subgroup. This is a really big task to be tackled because this is a fundamental, because already in the beginning of the InChI, there was a decision to just cut every metal to anything bond. It was just decided, and this is going through all the problems in the InChI, which InChI has with inorganics. And I think we will solve this in due course. Then there is, for example, a really active group dealing with mixtures. I mean, if you are buying N-bully or tertiary bully, that is nothing, it's not a pure compound, but it's normally in hexanes. And this has to be dealt with as well. For the going into the nanomer world, you don't have normal small single molecules, but you have rather large arrays, which has to be tackled. Then there's one group working on the reactions where Gerd Blanke is heading this group, which is also really cool to describe full reactions and not just the compounds. Then there's a group working on QR codes as another form of a machine readable code of an InChI, but also to develop educational material, training material. It's important. And finally, there's a new subgroup to bring the InChI into the GitHub. And hereby, I hand over to Gerd.
Yeah, and the GitHub group is actually run by me as well, and it's just me in the current moment. So we are growing. So if you just go to the next slide, you just see the status of the different groups. So in terms of polymers, the basics are done. If you think about polymer representations using brackets, so those structural repeating units or chemical repeating units, then with copolymer brackets to have more complicated ones. But there are some bracket types for polymers, like grafted polymers, that are pretty rare in databases that have not been implemented. But the standard parts seems to be done and is released with 105 and corrected. Some issues had to be corrected in 106. In the current development, you see that the main areas are organometallics, and a few words about that one later on. In terms of stereochemistry, we have proceed pretty far to something that we can work on and develop, especially if you think about the so-called enhanced stereochemistry or some special sugar chemistry. All of that is supposed to be described, and hopefully that can be implemented later on. Tautomers, by the way, is a set of, meanwhile, I think 112 rules how to handle functional groups in a unique way. And this unique description is pretty important to make sure that you really have the unique identifier you need for searches, for example, within databases to keep the uniqueness check of those systems. Isotopologues are developed as well. This is a pretty small area handling isotopes. There we are just discussing the input format. And what you see right now, those parts that are really under development, large molecules, is just in a status where we are just setting up the scope. It looks like that Helm is going to play a very important role in the further development of Helm, and that we have to find ways that Helm, that is not canonicalized in its representation, gets a canonicalization by InChI. And the variable molecules, the Marcouche InChIs, which is something between the representation of the mixture of xylene up to a full patent, is a discussion group as well. We have set up a first prototype, and now we're trying to get some more experiences. On the other side, on the right side, you see how far we are with the applied InChIs. Applied means in that case that we are just using standard InChIs and combine them to solve different purposes. Yeah, so obviously, first one was reaction InChI, that was mentioned already. Then we have test phases of the resolver. Resolver is actually the idea that you cannot go backwards from an InChI key to an InChI. But if you just have got an InChI key and you must get the InChI somewhere, the idea was to say, okay, let's find it somewhere in the internet if the InChI key is published and then get the related InChI to that. That's why it's the reason it's called resolver. The outcome of that one was a more general tool to link databases and database searches, which can be used for other stuff as well, and is available under the GitHub account over there, and it's ready for testing. And I think there are negotiations with Tupken to let them test. Similar to the QR code, that has run through the IUPAC acceptance, which means you just have to wait for half a year if anybody's got any objection. And if this doesn't happen, it can be published soon, very soon, I think. We are working on coding. So mixture InChI and reaction InChI have some similarities technically seen. Currently, we are working, we changed the reaction InChI to open source development on GitHub. So you see the link down there. You may participate if you've got time. And part of the work will be to take a substream to implement mixture InChIs. Yeah, so this is just done. And yeah, InChI developments are not that fast. Same over here, unfortunately. Last but not least, Nano InChI. This is a very active group that had a larger meeting about 3 months ago, meanwhile. Which is, as Sonja already described, a very, very interesting topic, because it's not only a mixture, it's much, much more. It's a combination of a mixture of different layers that are bound or not bound, that may have got outer surfaces where you find other molecules or not. So it's one of the most complicated areas I've seen up to now, but the group makes quite a bit of progress meanwhile. But there's one major difference to the other ones, or the other ones try to have a unique description and identifier for their materials. With the Nano InChI, it becomes more a group identifier. Yeah, so it goes down to the point that most of the companies do not publish all the information about their nanomaterials. And with that one, you can just point that this nanomaterial belongs to that group. And we have to see over there how much details are possible to be handled over here. Okay, on the next slide, we have unfortunately a very sad point that our developer died last November on Corona. And that was, of course, not expected and left us a little bit with a disaster. So Igor was, one of those geniuses that does not only work as a professor or worked as a professor for inorganic analytics chemistry at the Lomonosov University in Moscow, but was a great cheminformatician as well. And he worked in his ivory tower like most of the traditional developers. And once in a year, you just gave him some food, and a year later, you just got the outcome of that one, and you got a new release. Unfortunately, that happened when he was really finished with this work for a new release. And now we are a little bit in a tricky situation. So if you just go to the next slide, you see the current status we have. We have published the 106 release, and I just you can download it from the InChI Trust site or from the GitHub site, which I just have to release today. I just need a quiet moment. Besides that one, we got 2 sets of code streams of the actual coding that was done by Igor. And I just have to merge them to one code stream so that we can use it for the further development. Major parts that have been corrected since 106 were some memory leaks reported by Google, because Google is a heavy user of InChI, and but they have got quite interesting and quite strict security rules that we have to fulfill now, and they were mainly filled by Igor's work. So if you just continue on the next slide, our next point is that we have, well, actually, in the worst case, you call it a spaghetti code. It's not that bad. There are a lot of comments about that one, but we have to open the code to make it more readable and that it becomes much, much easier to maintain. The idea is to go to GitHub, yeah, and to have other people working on the code, you must present the code in a way that they are able to understand it, because otherwise any kind of involvement of the community will become pretty difficult. The main idea right now is to have a structure normalization preprocessor before you start with the real part, which is the canonization and connectivity, that you have got post-processing. Yeah, so that we're going to have 3 steps that are in the current moment are all within one big node together. The structure normalization preprocessor is pretty important to handle the tautomers, for example, because this is a pure structure normalization process in most of the parts. And even for organometallics, as described a little bit later, we need it. So InChI will move to GitHub, and on the next page, you just seeing the current GitHub page. Those are the addresses. As said, I just have to open it today. The first one, so that's the code. The second one, the development version, it's not fully finished. I'm still in trying to find out which of the 2 versions or which combination of the 2 versions is the best starting point for the development. Okay, so how do we continue now? In the middle of June, we had a meeting in Cambridge to discuss the further development, and there we had some ideas, and that's the outcome of all of the discussions. So we start with InChI 106, and we start with a prototype. The idea of the prototype is that a number of people can participate in that one, that we can test already quite a bit of things, like the tautomer transformations and the uniqueness behavior of the InChI once those transformations are run over those functional groups, before we have to fully implement that one. Out of practical test experiences, we have seen that we have to change some of the coding later on because we haven't thought about certain standard exceptions that they occur more often. And if we have a better overview about those things that have to be handled. It will help us to build a better version. And we can already test beforehand, before we are going to set everything into programming stones. The programming stones are found on the right side. Yeah, so we are not right sure how we are going to call the next version. It's very likely that most likely C++ becomes the programming language because all other programming languages do understand those tools. On the other hand, the issue over here is that there are not so many legacy programmers out there that can do this kind of work. And if you come down to the number of people working in the chem informatic area, it becomes pretty tricky and pretty expensive as well. Yeah, so those are some limitations we must have in mind as well. So while we are going to test, on the one hand, we are creating more traditional development methods that are nowadays standard. So please, not an ivory tower again, but let's have standard development using agile methods, so that we've got smaller sprints. Yeah, meaning you just work for 2 to 3 weeks. You define your work even for 2 to 3 weeks, and then after that time, you're going to test the stuff, and then you define what has to be done in the next round. This is standard nowadays, and it makes it easier to let other people participate, and the entire process is much more overseeable because people from the business, in that case, that means from the InChI subcommittee, are capable to follow up the process, and we just say, oh no, this development takes way too long and spends way too much money. We have to focus somewhere else. This kind of stuff can be guided much, much better. So on the next slide, we are just a few notes about the prototype. Tautomer transformation and organometallics are the 2 points we hope to address beforehand. We have the output formats for the enhanced stereochemistry. That is an internal issue because InChI up to now does not know the extensions that are necessary for that. That leads to the general point that we have to support V3 mol files. That request comes up from industry as well to let the InChI become fully the key for the industry to handle their internal databases. What they would like to get out of that one is that this is an open source development where they can participate and where they know what is going to happen. Thinking about tools, there are a few of them meanwhile. So Thomas Sander was a developer at Roche, I think, when you started, went to Actelion. Then Actelion was bought by J&J. His department became independent with another name. Sorry, I forgot that one. But he developed his own tools, and he's got his own normalization toolbox, which is called OCL. And he is responsible for the data warrior. Some of you may know that one as a tool. Then we've got RDKit, we've got KNIME, we've got ChemExon tools, and we've got BioVia. So all of them could be environments to work on. On the next slide, you find the example that Hina Gray set up to test the organometallics within KNIME with some tools that are using the ChemExon libraries to manipulate structures. And basically what you see on the left in the yellow part is that you have to read the structures. Then you come up to the structure manipulation sections, which are, I think, in orange and red, as far as I remember. And what we have to do over there, because we are talking about new bond types like dative bonds and coordination bonds, we have to translate it into a way that InChI is still capable to understand it. That's done over there. And then you just run the standard InChI process, but not with the standard parameter, but with a parameter called, oh, forgot it again, which let you not disconnect the metal atoms. You must have in mind that we have got around 20 or 25 parameters that can be set to run an InChI calculation, and only one combination of those parameters is the so-called standard InChI. Yeah, and the lower parts are just the output to be created so that you can read the InChI. This is a working prototype, and Hinak was able to show how the how the discussed alternatives for the InChI may look like, and how they can how we may use them. Yeah. So with that one, you start to get a look and feel how that looks like, how this may be used as well by yourself, because you get the first examples out of it. With that, we come up to the next slide and the organometallic status, which has made big progress, and most of the stuff can be implemented now. That especially means the acceptance of it's not on the bond type 9, it's which actually is related to the mole file format, which is presented by BioVia, but it's the bond type 10 as well. So we're talking about so-called coordinative dative bonds and haptic bonds. The haptic bond part is behind the accept multi-attachment bonds, which, you know, if you go down, for example, to a ferrocene drawing, where you got the bond pointing into the ring system, technically it's done on the BioVia side by having a star atom in the middle where the needle is of the stick, and just having numbers that make sure that you got the relationship between that star atom and the other atoms that it is related to. That's the technical background to that. But the most important point is that we agreed on the no disconnection. That means the bonds to the metal atoms are kept, which is pretty important, because otherwise we would not be able to handle any kind of stereochemistry. The exceptions is the traditional salt disconnection. Yeah, so if you've got sodium chloride, it will continue to be disconnected as you normally do within inorganic chemistry. And what is meant with the positive solution down there is that you are already able to develop this reconnection with a certain parameter within the InChI calculation, so that we can start to test it, how that looks like, and what type of differences we're going to have with the current standard InChI. The open issue that is still under discussion is the stereochemistry and how to do that. So in Cambridge, we came, John Mayfield, who was there, came up with a former presentation he had, which is basically mapping the actual structure into something like a cave that, or template, that's a better word, that represents a certain type of stereochemistry, like octahedral and so on. And then you've got a numerical process, which is pretty fast. Ola, who works for AstraZeneca nowadays, but was a professor in Heidelberg, I think, had another approach, and that's what is just being discussed in organometallics. But because we have got the other points solved, we can start the programming, and the stereochemistry is just seen as another point that can follow up in the post-programming. So where are we? You just, with the 9 part, you saw the first implementation of a rapid programming environment that has to be extended for tautomers. I have to work on the full requirement list and have to put that together. That means track all the enhancement and new developments and get them together and make sure that all of them work together, which is not necessarily given in some of the cases. And then we have to come up to typical project management parts, which is priorities of the next release, together with the subcommittee of the IUPAC, the full project plan and a roadmap when things are going to happen. So on the next slide, I think this is a comment that is much better given by Sonja.
Thank you again. Yeah, the problem is that the InChI needs to be programmed. So the InChI committees do a lot of work defining requirements, which bonds are important, how can we tackle ferrocene or multicentric bonds, as you already mentioned. But in the end, someone should program it. And yeah, by combining money from different projects, I have the possibility to hire 2 programmers. So it's 2 persons, but 1.5 programmers. It's perhaps a little bit more precise. And they will start their work in November and December and really start to implement the no disconnection approach for inorganics, which in the newest version of the InChI. And when this is running, in the same time, the committee can go on work on the stereochemistry, and then they will implement this. So it's a little bit a two-step process in this case. But as I heard from the nano-InChI groups and all the MinChI and RinChI groups, there is so much work to do that in fact, 1.5 programmer are not enough to make all the new codings here. And so the InChI is actively looking for more financial support, also from industry, to get more people technically involved here. But I think implementing all the inorganic part, where we now had long-term discussions, I think this will be done by the programmers then sitting in Aachen.
Yeah, and actually to let them do that, it means as well that we have to already work on the new code because it will be more or less impossible to do the changes in the old one, or very difficult. Please have in mind that 30% at least of the work is just related to testing. So each new release is going to bind a lot of people and work to that. Yeah, and of course, as you just found out, to hire people, we need money. We are trying to get more contacts into industry to make them aware about our current issue, that we really have to let InChI survive on a long-term run, that we really have to work now, and that they, if they are interested in InChI, we would like to ask them to support us directly. And with that one on the next slide, you just see the current supporters, and you find a new supporter, which is the University of Aachen. So thanks for joining the club. And those are all the people that are contributing or have contributed to the InChI development. Yeah, with that, thanks a lot.
Thank you, Gerd, for all the details.